Okay, so going to work with Marcus Sutter, and it's about intelligence as inference, that is all things intelligence, or that's most things intelligence, as just one inference mechanism. Since we know that in the brain, as Jeff Hawkins always likes to point out, it's in neocortex, it's just one mechanism that someone has to do everything, has to do all the work. So it's not like some optimization mechanism and some other some inference mechanisms. But everything seems to be done by one thing. That's one of the parts of this talk. And the other part is about Occam's razor, which is in general completely infeasible in its, if viewed as a proposition about the world. That is, the simpler things are more likely, at least if it's for every reference framework. So I'm going to focus this around the task of building a machine that simplifies the world. So that's one did quite a lot. It will be within a general reinforcement setting as we usually work within. So that means we're formalizing the AI problem as having sequences of actions, observations, and rewards. That agent takes actions, gets an observation reward back, and then it goes on in silence, like that. And I want to maximize expected discounted reward. I want to find a policy, which is here a function of histories to actions, which is different from what I talked about this morning about the state space, where it was from states to actions. But here, in the general setting, where you need a function from the whole history to actions. One defines the value function as expected return, and the single rational policies are the one that maximizes the value function for some Fourier distribution psi. And so the IX agent psi is defined as a mixture overall lower semi-computable environments, and then the value of a policy is actually interpreted as an intelligence measure that is with respect to that reference of Fourier distribution psi. So some previous work at last year's AGIs, we try to get around one of the main problems with UEI, which is the reliance on a reference machine. And first, by looking at the final set of reference machine and making an optimistic choice among them that includes some theoretical bounds. And then after that, have an infinite exhausting sequence where one keep adding to such a finite set, so that one, in the limit, exhausting all possible choices of reference machines. That's the last two, and one can in itself view those as learning a reference machine over time. So you end up picking one over time. But this time we go directly at the task of learning a reference machine that is suitable for the task for thing to try and solve. So one of my motivations, I said, was that Occam's razor cannot be true as a proposition, but work for all machines. For all machines, it cannot be true that simpler hypothesis is more likely, because simpler one machine can be very complex with respect to another machine. So, particularly since this intelligence measure has a finite effective horizon, you really get a complete reference machine dependence. So you get this politically nice result that any agent is super intelligent for some machine, but it doesn't really do that much for you. So imperative, what we view Occam as an imperative instead of as a proposition to learn a machine for which Occam's razor is true. So that's the way we view it here. The second big problem is the formula optimization, particularly since it's incomputable. It sounds like there's no hope for that one. But the idea of this talk is to simultaneously try to address both of these problems by constructing a machine for which good programs are short and for which good models of environment are short as well. So that on such a thing, it's much easier to search for good policies, for good programs, as well as searching for good models. So everything gets encapsulated in this inference task and try to infer a good machine. So the framework starts with a return function, in this case, a function from pro space all programs to R plus, to real-value reward returns, and I want to find the most rewarding program in the world. The return function might not be explicitly available, but might be valid for running the program. For example, in this arcade learning environment, I talked about this morning, with 500 Atari games. There's a sample of few games, and you get played in that, you get some return, and that is the return of the program, so you get it by running it. So this might include, for example, running speed. If you do it the way humans have to play an entire game, if you don't take an action, the game just goes on. And if you don't take many actions, of course, you get very low return. So actually having a higher return makes it a very practical measurement for what you're after. So for some return functions this might be a narrow AI, and for others it might be much more general intelligence. So what we do if you have a reference machine, we could, at least in principle, search a program by calling bits until we got a program that runs, and then observe RFP. So one has a program and try to run it. It might take some action, so it might not get run to take some action, but task will end, then you have some reward. And then what we want is to have a reference machine where there's high expected utility, high expected return. In this case, when we just conflict program on the input tape. So that is a task that we out to do now. So an example is if you have huge amount of math on the best program in the world, then things are very simple. You end up putting a theory on the input tape, and you have your AGI right there. You have it built into the machine over time. So there's one of several different procedures of doing this. We're going to use as some sequential procedure. We'll start with some machine. Let's say we have C, a programming language as a machine. And we could then suggest another machine and sample program from that and see the expected return and have a little bit more like a policy gradient method kind of thing. There was some work which it was good on learning inductive bias in a policy gradient framework in the early 90s already. Yeah, we can look at another result saying, well, the color is a bit unfortunate, but look at the sort of correlation between short length and high return and vice versa, long length and short return, by formulating that as expression in that inequality over there. So if one improves that, if the sum is over all programs that you care about, in that case you can guarantee that the expected utility of U prime is going to be larger than the expected utility of U. That is a generalization of something that exists in a much more narrow setting, something by Hinton, the relative payoff procedure from the 80s, I think. So that's in a very narrow setting, but the principle of why we get that guaranteed improvement goes through all the way to the universal setting. In practice, one of course need to approximate this with a set of programs on U. For example, we have a set of C programs, and then either a machine or people want to create a better programming language where it's easier to write the highly rewarding programs. So there's something already going on in the world. A lot of people are after such tasks where making program languages very easier to write rewarding programs. However, if you do perform this optimization of this expression, but with just a small sample set, then if you really form the optimization of all possible reference machines, then you can easily overfit by just putting all the mass on the highly rewarding programs, or the most rewarding of those programs, which will not do that much for you, because then you're somewhat stuck in what's already known. But in that case, in certain programs, you need to narrow the selection of the next machine by, for example, demanding that it has a limited implementation on the old machine. So you just put a bound on how large implementation a new machine should have an old machine. For example, how large can a compiler for a new language be written in your language might be C. So if you have a strong correlation with short length and high return, it guarantees a better machine if you have those old programs. So the good thing with this, using this inequality, instead of just trying the new machine, is you don't need to sample on the new machines. You don't have to build the machine. You don't have to figure out how long your programs will be on that new machine. So I would argue that this kind of development of a reference framework, which makes the world simpler or shorter to express, is already going on. It's going on for a very long time, but people doesn't care about AI. For example, developing a programming language, this is a very specific one, while also science at itself and mathematics at itself marvel at the simplicity of the universe, but this might be unwarranted. Perhaps we made it simple. Perhaps we just created all these concepts of physics, for example, that make some aspects of the physical universe seem very simple. We can express things in very simple ways, and then we can achieve some things, well, not others. Make something simple to do, some other things not very difficult to do, as we have chosen to build up our physics, for example. So science and language except create concepts that simplify the world, make it seem simpler, make some things much more tractable, while other things become more complex, but those things are very difficult to think about when you think in the frameworks that you're working with. So our human world of experience is constructed by Occam's imperative that simply is better, and both with hypothesis, but also the way it simplifies tasks. For example, the way I don't have to cook that much as long as I can order and pay at a restaurant is a simplification of cooking, for example. So one can ask here, are we talking about great AGI just through this process, regardless if you care about it or not? We're always perpetually having been up to this thing, at least for quite a long time. So for example, will the internet just increasingly wake up, as I said yesterday, by 7:10? Some others I couldn't quite figure out who the originator of the idea is. So perhaps, somehow, as things get simpler to express, you still need some perform the search development of the program somewhere on top of the framework, so it gets simpler task to perform this search. And it might also be very static AGI if it does not take over the improvement of the reference framework as well. If human beings still have to do it, it's somewhat a static AGI. But it might still be quite intelligent and achieve very high rewards on a lot of tasks, if not being as adaptive as another thing. But here we prefer to use both of these tasks into one task. One try to find an automatic way of improving the reference framework in some iterative procedure, where one try to help on with this task of creating new machines where everything is short run. So I argued for the imperative development reference machines that makes the world simple. It inspired by the planning as inference paradigm, which was perhaps not as clear in this talk, but clear in the next phase of the talk. But also in that case, you make fruitful actions more likely in such a framework. So instead of separating things into model inference and then optimization, you somehow do the whole thing at the same time, end up with a rewarding action being more likely, so your preferences are encoded in the probabilities. I will get that the process is already ongoing for a long time, and it might be accelerating because the simpler things get, the easier it might be to suggest things and make things even more simple. My current work is to try to move from these reference machines, these discrete programs. It's very difficult to search over programs in reality. I need very good language to even get started to be able to find something that runs at all. Right? If I just got a conflict programs, it's not going to work that fantastic in most of those languages I do got. So I used to work on mathematical programming now for quite some time. My current work is moving to using continuous parameter functions, like having done some experiments out of code as we just got started, and creating something that is counterpart to what I argued for here, which will be called a reward modulated inference framework, where you have some trade-off between what models promises high return and what are fitting data very well. So you can have two terms. And this is something that also connects some things that showed up in neuroscience, is reward modulated spike timing things, where the various models of neurals firing, and you can express them as having gradient update on some objective, where one term which dealing with expected reward that would be promised by the model, and another that deals with just unsupervised learning of the inputs. So also bring it back to this connection to the optimism that started this whole work. Making likable things more likely is indeed another way of expressing optimism, which I'm talking about in the last two talks. Thank you.